Alright, so what we're looking at here is a layer of paraffin wax that is congealing and solidifying over a layer of water. Blue dye has been water added to the water, whereas the paraffin wax has had no dye added to it. Throughout this experiment, you're going to see various attempts to move the layer of paraffin wax sideways. At first, the paraffin wax will be only the uppermost solid layer of the paraffin wax will be moving, but then over time, the paraffin wax will get thicker and thicker. What I want for you to watch over the course of this video is what's happening where the wax is being pulled apart, what is happening when the wax is coming together, and what is happening when the wax is sliding side by side, and try to notice features on this. This is a little bit of an analog for the early Earth. Earth, where we think we initially had a very, very thin lithosphere that initially cooled by radiation outer space, but then over time that lithosphere thickens somewhat. And I'm not going to say it's perfectly steady at this moment, but I will say that its variation is probably in thickness over the last few 100 million years is substantially less than what we probably had in the very early era of Earth. And this is to get you sort of thinking about how that changing lithosphere thickness over time and changing composition might possibly affect it. This is not a perfect model by any measure. It is just a something to kind of get you thinking about how layers of the Earth change and how one material can change consistency over time as it cools. And also how the thickness of that solidified layer can affect the larger behavior of the solid layer. Now, you probably noticed at some point I added something in there. That was a glue stick from a glue gun. I was hoping to create subduction. We'll see if it worked. So what you're witnessing now, that white powder, is a mixture of citric acid and acid tablets, calcium carbonate. What I was hoping to get happen here was hoping that would be dense enough to sort of break through the outermost layer of wax and then react with water, create gas, much in the way water in the ocean floor reacts with rocks in the mantle, creating magma and gas. Essentially, I was trying to get some kind of like analog for the arc trench system in here. It didn't work as well as I'd hoped, and by this point the paraffin had hardened a thick enough layer that I was having trouble getting it to quite bend, so I had to do a lot of other manipulation. One thing I loved at this point in the video was watching the sort of paraffin wax congeal every time I cut a little slit. And this is kind of akin to what you see at mid-ocean ridges. You can get rifts in the absence of magma. You can get divergence. Certainly, there's evidence to suggest when you have hot material present, the rifting plays out a little bit differently, and there's a huge debate among people who study this more closely. But I love the fact that the minute you take two pieces of paraffin over molten paraffin and pull them apart, more molten paraffin from below comes up and hardens. So you don't actually need any additional source of heat. You just need more material to replace the paraffin that gets pulled away from that rifting center. So watch closely. So upon closer inspection, it looks like we did get some bubble formation, just nowhere near as much as I'd hoped for from this reaction. Yeah, that's sometimes how it is. And I was hoping maybe some of the bubbles would make some of the paraffin a little less dense. I'm going to try this a couple more times in other lab rooms. We'll see if it works better at one of those places instead. Alright, that's about all I got here. So we're starting to get to where I'm about to be able to show you some more plate boundary processes. I finally decided to start cutting squares in here. What became more obvious upon reflection is it's a lot easier to create things that look like the surface of Venus than it is to create features that look like the surface of Earth using the technique I've done here. Still trying to figure exactly what I might do to create something more Earth-like here, but that was certainly a thing. I also noticed that, like, I kept getting these large areas where molten wax went everywhere, and that would be akin to what we call flood basalt provinces or large igneous provinces. We don't really have any modern analogs to those. The most recent large igneous province is the Afar Triangle in Africa near the point of Yemen. Basically, the entire country of Djibouti and Eritrea and parts of Ethiopia and Somaliland are all parts of this sort of large igneous province. And definitely there's decent volcanism, but there have been periods of time where there was volcanism on a much larger scale. We kind of see that in this model right here. So again, is this perfect? Maybe not, but keep watching, see how it evolves, changes, and check out the photographs. Hope you enjoyed this little journey down Model Lane. One of the other sort of challenges and great questions about the early Earth is how and when did subduction start, and did subduction, when it started, look like subduction we have good data for now? And there's definitely a number of camps that suggest subduction has started as soon as there was a solid crust. Other arguments suggest it started substantially later, and even more suggest that initially it was shallow at points. One of the things I found when I was trying to do this is that this is probably my best shot here in the video of getting subduction, is that I got a wide variety of subduction behaviors when I pushed the pieces of wax together. Sometimes wax will kind of like go float, and you can kind of see on the left there is a little bit of a ridge popping up there in play sometimes. That was a success. If I could get anything like that, I was kind of happy. But there are subduction zones that don't really produce substantial mountain ranges, or those mountain ranges barely rise above the sea surface presently. Great example of this is Tonga, where we had that mass volcanic eruption a couple weeks ago that send a tsunami all the way here to San Diego. But there are other places where subduction is building some of the taller mountain ranges on the planet, and we've seen even areas where there's evidence for long-term subduction without mountain building, and then suddenly something switches and mountain ranges start to pop up. And I was just noticing this is like, at points I was even having trouble getting the subduction to even go down sometimes. I have trouble forcing it. I try to... It was a lot of fun, I mean, playing this. But there's definitely... What you want to get a mountain building is subduction that does, in some way, substantially thicken the crust on the overriding plate. There's clearly some kind of sweet spot in that where that is the result you get, but there's plenty of places where that is not the result you get. And this is one of those, we can explain mysteries, that is, we can explain individual locations, but a coherent explanation worldwide is a little trickier. So we're approaching the point now where the wax is hardened through most of its thickness. Interesting enough, we start seeing some very different behaviors when we start swooshing the plates together here and tearing things apart. So that was kind of cool. I want you to think about what would happen if this wax were a heavily cratered surface. And what would happen if the rate of cratering were to decrease over the time frame of this video? What would happen to those craters on the surface? Where would you see lots of cratering? Where in this video would you see the crater, would the surface appear substantially smoother if the video had started during a period of heavy cratering and ended during a time of much fewer impacts per unit time? And that's really the big thought experiment. All models are flawed, some are useful, but I hope this model's been useful to you somehow, and hope you enjoy the rest of the video.